Hello students, the next topic that we are going to discuss is about timing and delays for any hardware circuit. So any circuit have to definitely undergo the functional verification as well as the timing verification. We know that the functional verification is meant to check in order to know whether the designed circuit is behaving properly according to the specification or not. Okay, but in practice, any hardware circuit is accommodating a number of modules or blocks, and in the developed real hardware circuits, we also may have the logical elements also. So because of which a circuit may or may not give its functionality in the expected amount of time. That is, I can say that the designed circuit have to meet the timing requirements also. Okay, so as the timing and delays are controlled and also specified in Verilog module itself. Okay, now let us see what are the timing delay modules we are having in our Verilog HDL. We will discuss them in detail. Okay, so let me also add here one more point, that is time verification is highly required for any sequential circuit, because functional verification how it is important, in the same way the timing verification is also playing a crucial role for any designed hardware circuit. Okay, now we are having here the delay models. So what is the purpose of the delay models? Okay, so delay models are nothing but, here you can see here a point I have mentioned in the PPT slide. Blocks in the developed real hardware circuits associates delays with them. That means I am having a circuit. If that circuit is developed by a many number of logical elements or a modules or a sub blocks, definitely each and everything is going to consume certain amount of delay. Like as soon as I am sending the input signal, I cannot expect the output signal at the same instant of time. Certain amount of time definitely it will take place, and after that output will be coming as a or exhibited. So that means the real hardware circuit is associating delays with them, either because of the logical elements as I have mentioned, and also because of the data parts. So what are the data part? That means from start, like you are having a input signal. That signal have to undergo many number of sub blocks or modules or blocks. That means it has to follow some particular wires, or I can say it as data part. So that means it is undergoing a many number of data part. So like I am having here two blocks, block A and block B. So these two blocks are connected with a wire. This wire is nothing but data part. So for traveling from block A to block B, it is consuming, that means the signal is consuming certain amount of time. That means a delay is also a delay is also exhibited, not also by logical element, also by your data part. That is the difference. Now we are going to study the delay models in detail briefly. So the delay models are classified into distributed delay, lumped delay, pin-to-pin delay. In the distributed delay, I have taken here a logical circuit, a schematic, which consists of, in the first level I am having here two OR gates, and in the next one I am having here one NOR gate. So you can able to see here in the schematic, the delays are assigned based on per element, because this is one element, this is logical element, this is also a logical element. That means here the delays are associated on per element basis. That means delay values are assigned here to each and every individual element. So now according to the distributed delay, we are modeling this circuit by assigning the delay values to individual gates So this kind of technique, that is assigning the delay values to each and every logical element separately, is nothing but distributed delay, because in the term itself you can notice that the delays are distributed for each and every logical element. So if this is the thing, how to model the schematic by using Verilog HDL language? Okay, so let me, because this is my distributed delay, so this entire circuit module name is D and DD I have taken. Outputs is Y, inputs are A, B, C, D. Okay, so in the intermediate wires I am having here E and F. So if I want to realize the circuit using structural abstraction, this is the way, like OR gate, OR gate, NOR gate. So hash 5, hash 7, because A1, this is my first OR gate, this is my A2 is the second OR gate, and A3 is my third OR NOR gate. Sorry, it is a NOR gate. So A1 consuming 5 seconds amount of time to give its output to the wire E. A2 is consuming 7 seconds to give its output F to the wire F, and A3, that means NOR gate, is consuming 4 seconds of time to produce the output as Y. So this is the way of structural development. And coming to your data flow abstraction, we definitely going to use the assign as keyword. So you know how to write the instructions in data flow abstraction level. So in this way the distributed delay is described. The next one is lumped delay. So what is this lumped delay? The concept of lumped delay is very different when compared to your distributed delay. As here you can notice, the delays are specified only on a per module basis. So here I can able to find only a single delay is present as a delay on output last logical gate or a last logical element in a module, because it is my module. So what is my last logical element or a logical block? This is the NOR gate. So a single delay is present, that is given to your last logical element in a module. So in this case, this delay is nothing but the cumulative delay of all the parts in is lumped at one location. So you can see here in the previous diagram. So like a signal from A to a signal from which is at A, it have to reach to Y, means it is consuming certain amount of time, that is 9 seconds. Similarly for B. But coming to C and D, this C to travel to Y, it takes 11 seconds, and similarly for D also. That means what is the maximum amount of time such that your output will be fulfilled. So that means your output is expressed in terms of all the inputs. That means you are going to get the perfect output after 11 seconds, right? That means it is the maximum amount of delay, that is 7 plus 4, this entire module is offering to us. That is the maximum delay from any input to output is 11 seconds here. So this 11 seconds is dumped, is this 11 seconds is entire delay is lumped on output gate or output logical element. So this is about lumped delay. So like we can also realize this is entire schematic using the structural or using the data flow assignment also. So here I don't have any delays associated with this gate or this gate. I am having only one delay. This delay is related with the output logical gate, logical element assign hash 11 y equal to E and F. This is what happening in the program. So then the very next one is pin to pin delays. So delays are assigned individually to parts from each input to each output here, because let me explain you. As in the earlier cases we do have the distributed delay and lumped delay, but coming to the pin to pin delay, it is a third method of delay specification for a module. That is, Here what happens, assigning the delay values individually to part from input to each output. How many inputs are I am having here in the logical schematic? 4 inputs. So 4 inputs, each input is traveling towards the output. Okay, that means can I say I am having here 4 data part like A to E to Y, B, E, Y, C, F, Y, D, F, Y. That means delays are specified here for each input output part. So that means part A, E, Y, what is the amount of delay? It is 9 seconds. Similarly for B, E, Y, and coming to C, F, Y and D, F, Y, it is taking not 9 seconds, it should be 11 seconds. Okay. I wantedly hadn't changed this one, keeping in your mind that you people will notice this. So this is about pin to pin delays. So sometimes these pin to pin delays we call them as a path delays. So and this path delays is having a tremendous usage that you can able to see in the succeeding sections actually. Okay, so let us discuss those things also here. So path delay modeling. So according to path delay modeling, we need to undergo certain terminologies like specify blocks. So inside the specify blocks, it is full connection as well as parallel connection. These kind of terminologies also we need to focus on them. So what is a specify block? Now, a delay between a source pin and a destination pin of a module is nothing but a module path delay like AEY, BEY, CFY and DFY. So, path delays are assigned in Verilog with the keywords specify and specify. So, these are nothing but the statements within them, that is specify and specify constitute a specify block statements. So the inside the specify block statements only we can able to find the path delays for a given module. So let me discuss once again. I am having here 4 different parts. So these parts have to be mentioned only inside your specify and specify keywords or Verilog constructs. So from A to Y it is taking 9 seconds, B to Y it is taking 9 seconds, C to Y 11 and D to Y it is taking 11 seconds amount of time. So can I say that this kind of arrangement within the specify and specify block are nothing but the parallel connected network. Okay, and one more point it is to be noted here, these specify blocks are separate blocks which does not appear under any always or initial statements, because these are very separate block and always meant for like defining the path delays inside it. And so here every path delay statement has a source field, you can see, and a destination field. Okay, so a parallel connection, I said you that this is a parallelly connected, that means inside your specify and specify all these statements are parallelly connected. So a parallel connection is specified by the symbol equality. You can see here parallel connection is specified with the symbol equality greater than is used. That means I am having here a source field or a source pin and destination pin, in between them equality greater than. This indicates that it is the source and destination are parallelly connected. So how much amount of delay a source to destination the part is providing, the part is exhibiting is given by the delay value in this manner. So this is about parallel connection. So you can have a question here like in parallel connection each bit in a source field is connected. So here I am having here this is my source field. Let me call this one. This is my source field and this is my destination field. Each bit in a source field is connected to corresponding bit in the destination field. This is the concept of parallel connection. Okay, but if the source and the destination field are vectors, so if the source is a vector, destination is a vector, that means they must have the same size or same number of bits, because here x and y are nothing but both are scalar quantities, but here in this one x and y, which is a 4-bit vector quantities, these are. So the parallel connection will be for corresponding bits itself. That is the difference between a scalar and vector parallel connections. Okay, in the parallel connection, the source field and the destination field should be of equal size. If the source field is, like for example, x is a 3-bit vector and y is a 4-bit vector, I cannot establish the parallel connection. This is about parallel connection of a specified under the specified blocks. Next is full connection. So what is this full connection? It is similar in syntax with your parallel connection except at this area. Like in the parallel connection we do have equality and greater than symbol, right? Here we are having star and greater than. So a full connection is specified by the symbol star greater than. That is, the syntax will be followed like this: source field star greater than, destination field equal to. What will be the delay value? So what is the purpose of the full connection then? In the full connection, each bit in the source field is connected to every bit in the destination field. Like if the source and the destination are vectors, they need not have the same number of bits or the same number of size. It is not required as it was in previous case. So we may have different number of bits at source side and different number of bits at destination side, such that every bit in the source field is getting connected with each bit in the destination side. A full connection describes the delay between each bit of the source and every bit in the destination. Like here each bit in the source, and here I am having, according to this module example, I am having here 4 input signals, and this is my y is my output signal or a output field, destination field. So can I write the syntax in this manner? Because full connection or parallel connection, definitely they need to appear in between the specify and the specify blocks. Now source fields are what? A and B. So A to Y and B to Y, they are consuming same amount of time. So A is connected to Y, B is connected to Y, C is connected to Y, and D is also connected to Y. So A comma B star greater than, that means parallel connection I am doing here, out equal to 9. C comma D star greater than, out equal to 11. So this is the amount of delay. 11 seconds is the amount of delay for C source and D source to have it apart C, F, Y. This much amount of delay, 11 seconds it is consuming. Now I am having here a question, like if input is 4-bit, x3 down to 0 is a 32-bit vector. It is not a 32-bit vector. I have written wrong. If input x is a 4-bit vector and output y is a 2-bit vector, and so here I am having 4 pins, and here you can able to find 2 pins here, or 2 destination pins and 4 source pins. If I want to have a fully connected network between the source field and destination field, such that each bit at the source field is taking 5 seconds amount of delay for its part from source field to destination field. So how many number of fully connected network do I require, or how many number of parallel connections do I require? Source side I am having 4 pins, destination side I am having 2 pins. So how many number of parallel connections I require here? That is 4 cross 2. such that each and every part in your parallel connection is taking 5 seconds amount of time as its delay. And the next concept is spec param. Sometimes in our Verilog language, special parameters are very important, as these can be declared only inside your specified block, and we do use here spec param as the keyword. Okay, so what is the main meant for the spec param is hard-coded delay numbers. These are the hard-coded delay numbers to specify pin-to-pin delays. Okay, like it is common to define the specify parameters by using the spec param statement. Okay, so specify let me have one example here so that you can understand this concept clearly. So I am having a D flip-flop here. The input for my D flip-flop is D and the output for my D flip-flop is Q, right? So according to the spec param, first thing is spec param D to Q. That means from D to Q a part will be established right inside it. So that part is taking 9 seconds amount of time. And next, from clock to Q also, because each bit in source field is getting connected with each and every bit in the destination field. Okay, now the clock to Q also will be having definitely a part, and that part is having 11 seconds amount of delay. Now, so this is according to the parallel connection from D to Q as well as clock to Q. So we know the syntax of parallel connection, that is source equal to greater than destination, source field equal to greater than destination field. What is the amount of delay value that will be specified here? From D to Q it is having 9 seconds amount of time. From clock to Q it is having 11 seconds amount of time. Okay, so for example, in future, if D to Q and clock to Q, the part is providing some other delay that are not matching with its previous values, so we can just have a change here itself only. Okay, such that if these values are changed here to this assignment, so this assignment can be assigned to D to Q as well as clock to Q. No need of changing everywhere inside your program. Like for example, D to Q, the new value from the part from D to Q is taking 14, and then the new value for the part from clock to Q is taking 16 seconds. So inside my program I no need to change many a number of times. Simply I can change the value here itself. So once I change the values, this is assigned to D to Q variable. Like how do you have the text macros? So the text, this is the text of, this is the text and this is the macro name. The text is given to the macro name. Wherever you are going to find the macro name, it is being replaced by the text of the macro. Okay, similarly here, like for the def param we have seen in our earlier classes, right? In the similar manner, whenever a updated delay part, I meant to say whenever your part is updated with a new delay, I just change the value of the delay here. No need of changing in the entire program. As if I have changed it here, this is assigned to this one, this is the variable that is going to store the value, and this variable is contributing how much amount of delay this part is exhibiting. So this is about spec param statement. And the next one is timing checks. So what are the timing checks in our Verilog language? What is the purpose of it? So the main intention or motto for specifying the part delay is just to simulate the timing of the actual digital circuit. Okay, here we are not using the gate delays, like how much amount of gate, because we are mainly focusing in the only on the part here, because once we are focusing on the part, the elements or the logical elements comes under the part itself only. So no need to exclusively consider how much amount of delay particular logical element is contributing for generating the output product or output signal. So I can say here actual, so the part delay, whenever we are considering, we are not going to keep an eye on the gate delays, okay, because part delays are only giving better accuracy as it covers the entire things in a module. Part delays can consider entire thing from source pin to destination pin. What is the part, what is the signal, the signal is undergoing, it is undergoing to, or it is passing through what logical elements or the logical blocks, everything. The part relay will be focusing on all the entire things. That is why we will get the better accuracy. Coming to the timing checks, these are definitely required for our Verilog HDL timing simulation for a sequential circuits. So if any timing constraints are violated during the simulation, in order to check timing constraints, for example, I am having here an arithmetical logical circuit, or simply an adder. You can take as an example of an 8-bit triple carry adder. So I expect that the circuit definitely takes 6 seconds amount of time to produce the output, but 6 seconds I have kept it as a maximum value. Minimum value is 2 seconds. So if it is producing me or giving me the output above 6 seconds, means it is violated. The circuit is under violation. Timing constraint, it is not meeting the timing constraints. So here timing checks are meant to see if any timing constraints are violated during the time of simulation. And these are very, very important for any high-speed sequential circuits like finite state machines or microprocessors, or any kind of circuits where a clock is required. Now, so for the timing checks, we sometimes call it as a flip-flop timing. As I have mentioned you, these timing checks are meant only for the any circuit that is having clock as its associate member. Now, can I say it is a sequential circuit? The timing checks are applicable for that sequential circuit, in the sense nothing but a flip-flop is our basic element here. So flip-flop timings we call it as. Now the flip-flop timings, nothing but here we do have timing check system task as $setup, $hold and $width, which are also specified inside your specified block. Let me discuss about each and every timing check here, that is setup time, hold time and width or period. So what is a setup time here? The setup time is nothing but it is the minimum amount of time the data, because for a flip-flop I am having here, D flip-flop I have taken, D is the data signal, Q is the output signal and clock is a signal, that is C signal or a reference signal. The minimum amount of time here, the data signal should be held stable or steady before the clock event is happening. So this is my clock signal, this is my data signal. So the clock event is happening somewhere here, like from logic 0 to logic 1. This is an event, the clock is undergoing. So at this time or during at this instant of time, And before this, your data signal should be held steady for certain amount of time. That is, the data should be held stable before the clock event so that the data is sampled by the clock. That means this data is sampled by the clock. Okay. So the amount of time the synchronous input D must be stable before the active edge of a clock. We call it is a setup time. We call this area. So you can see here TSU I have indicated here. We call this one as a setup time. So that means during the setup time your data signal should be very stable and steady before the rising edge of a clock. Then what about hold time? Hold time is, it is the minimum amount of time the data signal should be held stable even after the clock event. So after the clock event, that means from logic 0 to logic 1, an event had taken place. After this event also your data signal should be stable for certain amount of time after the clock event. So that the data is reliably sampled. Okay, this synchronous input, that is D, should be held stable after the clock edge, after the active edge of a clock, and this we call it as a, this duration of time we call it as a hold time. Okay, this is hold time. And the next one, so what are the setup violation and hold violation? As I have said you that any sequential circuit have to definitely undergo the timing check, that like timing verification is required. I meant to say that the circuit is giving the output according to the expected time or not. If it is not giving the according to the expected time, means something has went wrong in the schematic or in the module or in the subblocks or wherever, something in the hardware there is a fault, we can say, if it is not meeting the this given constraints. So whenever any design is not meeting the design given constraints, we can say that as a violation, the circuit is violated. So here we have two terminologies. One is setup violation and the next one is hold violation. So if setup time is TSU for a flip-flop, you can see here, and if the data is not stable before TS, because you can see this area as well as this area, you are having here cross lines, right? That means this is not a stable data, it is a fluctuating data, and the stable data, it may be a 0 or it may be a 1, but here in the D and here in this shade as well as in this shade, I cannot know whether it is a fixed logic 0 or logic 1. Okay, now according to setup violation, so if setup time TSU is a for a flip flop, and if the data is not stable in this during this region, that means before the active edge of a clock, then the circuit is under violation as the data is changing in the non-shaded region, that is before the active edge of a clock. So that means I say that my D flip-flop is under violation if data is changing in the non-shaded region. Yes, that means D flip-flop is under violation. Similarly, according to what is hold violation, whenever we know that the hold violation duration is THD or the time is THD, and during this time for a flip-flop the data should not change. If the data is changing in this part of non-shaded region, that is after your active edge of a clock, then my circuit is undergone to violation. That means my flip-flop is violated. And if the data is changing in the non-shaded area after the clock edge, I can say it is a hold violation. So these are about setup violation and hold violation. Once have a glance on this PPT slide. Okay, so then definitely if there should be some keywords in order to have or in order to know about these timing checks. Okay, what are the keywords? We do have here dollar setup task. Setup checks can be specified, like setup violation is there or not. These nothing but setup checks can be specified with Verilog construct or Verilog keyword or a system task, that is dollar setup. So and the syntax you can able to see here, dollar setup, data event comma reference event comma limit. So here in the diagram, D is nothing but data event and data signal. For this data signal, data event will be there, and C is nothing but reference signal or the clock signal, and for this clock signal, reference event will be there. That means clock signal is having reference event, data signal is having the data event. Now what is an event? Like moving from some point to other point is nothing but an event. So in this diagram, let me tell you that the data signal at this point, let me call it as a 2 seconds, this is 4 seconds and 6 seconds. So clock event or the reference event is happening at 4 seconds, and similarly data event is happening at 2 seconds, and here up to here and this point, let me call this one is a 6 seconds. Okay, so at what time there is a transition happening, we call it as a event. Now, so this is dollar setup, data event comma reference event comma limit. So like when violation is reported, whenever your reference event time minus data event time is less than the limit, this will be provided by the so this will be provided in a data sheet sometimes. Now reference event minus data event is less than limit. Whenever this equation is happened, we call that circuit is under violation. So I am having here a D flip flop. For example, 4 D flip flops I am having here, and for the D flip flops A, B, C, D, this will be the clock signal, this will be the data signal, clock data and clock data for the 4 D flip flops. In the first D flip flop like waveform window, reference signal is this one, data signal is this one. So reference event is happening at 2 seconds amount of time, and data event is happening at 0 seconds amount of time. That means from what time onwards your data signal is stable. Okay, from 0 seconds onwards, and reference event is happened at 2 seconds. So reference minus data is less than limit. Limit is 4. They have already given to you. So 2 minus 0 is less than 4. That means it is under violation. Second, coming to B. So reference event is happening at 4 seconds and data event is happening at 0 seconds. 4 minus 0, it is less than 4. That means it is also under violation. Coming to here. Reference event is taking place at 3 seconds. Data event is at 0 seconds. So 3 minus 0, it is less than 4. Hence violation. Coming to fourth flip flop, that is D flip flop. Reference event is 9 seconds, data event is at 4 seconds, 9 minus 4 is 5 less than 4. That means this circuit is not undergoing any violation, it is violation free and meeting the timing constraint. So in this way we can able to find out whether any circuit or a setup is undergoing setup violation. So this is all about setup violation. And coming to the hold, how to check the hold violation, like there will be a hold task also will be there. How we are having here the setup task, in the similar manner hold task will also be there for hold checking. So hold checkings can be specified by the Verilog construct, that is $hold. So the syntax will be reference event, comma data event, comma limit. So why the syntax is like this means in the setup task you are having the syntax like this. Setup time is nothing but before the rising edge of a clock. That means this area I need to concentrate, or this area I need to concentrate. That means here data event is happening first, next reference event happens. So that is why in the syntax data event, reference event and limit. Coming to hold check, reference hold check is nothing but after the active edge of a clock, that is we are going to perform the hold check, or hold violation is there or not, we need to find out. So hold is after the rising edge of a clock. So which one came earlier? Reference event. Next data event came next. So reference event comma data event comma limit. So how to know whether my circuit or the flip-flop is under violation? Data event minus reference event is less than limit. I can say my flip-flop is violated. So here 3 minus 2 less than 3 violated, 6 minus 4 less than 3 violated, 7 minus 3 4 is less than 3. No, it is not violated. That means this circuit C flip-flop is having or meeting the timing constraint, hence it is free from the violation. Coming to D flip-flop, so 12 minus 9 3 is less than 3, hence it is violated. So in this way the hold check can be performed for any sequential circuit which may have a enormous number of flip-flops. But for our simplicity I have taken here a simple D flip-flop for your understanding purpose. Okay, and the next flip-flop timing concept is worth. So worth check is also sometimes important and plays a good role for a sequential circuits. Like sometimes it is necessary for us to check the width of a pulse. Okay, like we have here $width, that is a system task used to check the width of a pulse meets the minimum width requirement or not. A minimum width, like during the duty cycle, the minimum on period, it is meeting the minimum on period or not, or it is undergoing minimum off period or minimum on period, set period we call it as. Okay, so in order to check that one, we use the $width syntax. The $width keyword or the system task, and the syntax will be $width reference event comma limit. So you may ask me a question, sir, why there is no data event in the syntax? You can ask me like this. So the main reason beyond it is we are checking the width of a pulse itself. In this case we are not monitoring, like as in the case of your what yeah you have here in the case of setup and hold times, right? That means here data event is nothing but a signal that is monitored for violations. Reference event is nothing but signal that establishes a reference for monitoring your data signal. Reference event is nothing but it is monitoring the data signal, but here a data event is nothing but it is a signal that is monitored for violations. It is monitored for violations. The reference event is monitoring the data event signal. Understand the difference here clearly. But coming to $width case, we don't have this requirement because we are mainly concentrating on to check the width of a pulse. That means T on is T suffix on, it is meeting the minimum pulse requirement or minimum width requirement, it is meeting or not. That is our main motto. So like I don't feel any necessity because reference event is okay for me to check, or the clock signal or a pulse signal is okay. Any pulse signal which may be a data or it may be a clock is okay to check the width of a pulse. So here reference event, it may be a clock or it may be some other signal. Okay, I am not saying it is only a clock signal, it is some other variable signal also, like which is having an edge triggered event. With this reference event is reference event signal. Reference event is nothing but this should undergo an edge triggered event. Some variable or some signal has to undergo the edge triggered event. So whenever it is undergoing any edge triggered event, we call it as a reference event. Okay, and limit is already will be given by the given to you in the specification sheet, and limit is the nothing but minimum width of the pulse. So it should meet the minimum width of the pulse. Okay, now the data event, why it is not specified explicitly for dollar width is, the reason beyond this one is the data event is derived as the next opposite edge of your reference event. For example, if this is my reference signal and it is my reference event, so it is an upgoing, like it is a leading edge, it is my trailing edge, right? So it is going from logic 0 to logic 1. The next opposite edge will be this one only, right? So this is my data, this is my data event. Hence the data event is not specified explicitly for dollar width syntax, so it is considered as the next opposite edge of your reference event. So this is my reference event of this clear signal and this is my data event. So does dollar width task checks the time between the transition of a signal value, because here I am having a transition, right, to the next opposite transition in the signal value. This is one signal value transition, means the next transition, the next opposite transition will be here, you can able to find. Then when will be the violation reported? Violation is reported when data event minus reference event is less than limit. So if I said that edge reference event is happening at 5 seconds, data event is happening at 10 seconds. So 10 minus 5 is less than 6. That means this is violated. So that means minimum pulse, like width of the pulse, minimum width of the pulse also it is not meeting. So I will be having my width violation. So in this way the flip-flop timing checks can be described for any sequential circuit or any finite state machines which definitely accommodates a clock signal, or for any high speed sequential circuits. Okay, thank you for the day.